All right, everybody, we're back for part 2 of lecture now. And as you can see, we're going to start chapter 10, and we're going to start, and the subject of chapter 10 is alcohols. So first, let's just remember what functional group we're talking about when we say alcohols. So what is the structure of an alcohol? Well, really what we're looking for is an OH group, a hydroxyl group, attached to some R groups. Okay, so we'll just label these arbitrarily as R1, R2, and R3, where those R groups could equal hydrogens or alkyl groups. Okay, and whether they're all hydrogens or all alkyl groups, we'll change the classification. So remember, we could classify alcohols as primary, secondary, and tertiary. We learned how to do that way back at the beginning of class. Okay, so what is some of the hallmarks of this, alcohol? Well, one is that the carbon that the OH is bound to is sp3 hybridized. And then something else, as we'll be referring to this a lot, the OH is referred to as the hydroxyl group. Okay, so there are other functional groups that can contain a hydroxyl group, but those functional groups are not fundamentally alcohols, meaning they have different properties and reactivities. Okay, so let's just think about some other functional groups that are not alcohols that contain hydroxyl groups. Okay, so can you think of any groups that contain, or any functional groups that contain OH, a hydroxyl group, but are not, an OH attached to an sp3 hybridized carbon? So one of them would be phenol. Okay, so that's really in its own class of functional groups. We also have carboxylic acids. So notice in both phenols and carboxylic acids, we have the carbon that bears the hydroxyl group is sp2 hybridized. Okay, so here we have a carboxylic acid. And, one of the hallmarks of alcohols, one property we could think about is its acidity. So the pKa of an OH in an alcohol is roughly, 15 to 17, whereas a phenol is around 10 and a carboxylic acid is around 5. So clearly there's one property that is distinctly different between, those not alcohols and our alcohols. Okay, and then one other one we could point out is we learned back in chapter 7 of this unique functional group, we were talking about tautomerization. So this was called an enol. So if that carbon, so this carbon that our OH is attached to is not sp3 hybridized, it's not an alcohol. So like in an enol, that carbon is sp2 hybridized, and it's part of an alkene. So there's differing reactivities as compared to the alcohol we're going to talk about. Okay, so that's an alcohol. So let's go ahead and learn about how to name alcohols, and then we'll come back and start to think about some of the other properties of alcohols. Okay, so at the beginning of naming, I just want to revisit the functional group priority list that's in our nomenclature packet. Okay, so notice where we are with alcohols. Okay, for the purpose of this semester, alcohols will be the highest priority functional groups that we learn. So ketones, aldehydes, amides, esters, carboxylic acid, everything above that you'll learn about in Organic 2. And so for our class, alcohols will be the highest priority functional group. And remember what that means for IUPAC rules. That means that the alcohols are going to take the priority in terms of numbering the parent chain. Okay, it also means that the ending of the name should take on this OL ending, right? So alcohol has that OL ending. Okay, so let's go ahead and start to look at the rules of naming alcohols. Okay, so the first one is that we are going to go ahead and number the parent chain so that the carbon that bears the OH group is part of the longest carbon chain. And we want to number that parent chain in such a way that the carbon atom that bears the hydroxyl group has the lowest number. Okay, so even in the presence of alkenes and alkynes, since alcohols are the highest priority functional group, we want to give the alcohol carbon the lowest number. Okay, and then we're going to change the suffix of the parent alkane. And this should really say of the parent alkane, alkene, or alkyne, because it'll depend on if we have double or triple bonds, but we're going to take that E ending from the parent alkane, alkene, or alkyne, and we're going to change it to OL. Okay, and then how we're going to indicate the position of the OH group within the molecule is going to be, we are going to indicate it by the number before that OL ending. Okay, so let's go ahead and practice that with these molecules that we have here. All right, so we can clearly see that the hydroxyl group in this first molecule is closer to the right-hand side of the carbon chain. And so it would make sense then to start numbering at that right-hand side. Let me give myself a smaller pen. Okay, so we're going to start numbering at the right, and we'll number towards the left, and that gives the alcohol the lowest possible number. Okay, so we still want to find the longest carbon chain, and then the carbon that bears the OH needs to be part of that longest carbon chain. Okay, so then if we're looking at this molecule, we can go ahead and name the substituent information up front. There are chiral centers at carbons 3 and 4, but since the wedges and dashes aren't shown, we wouldn't be able to assign the RNS, so we don't need to include that in the name. Okay, so here we have 4,6-dimethyl. That takes care of all the substituents. And then we want to think about the root name. So the root name or the parent name of a 7-carbon chain is heptane. Okay, so we're going to have heptane. We're going to remove the E ending and change it to OL, but we need to indicate the position of the alcohol. So it'd be heptane, remove the E, and then 3-OL. So the carbon that bears the hydroxyl group is at the 3rd position, so it's 3-OL. So 4,6-dimethyl heptane 3-ol. Okay, so the next example is, basically the same molecule, but we've added a carbon-carbon double bond. I want to show you that in this example, it doesn't matter that we have an alkene present. It's not going to change the fact that the OH is still the alcohol is the highest priority functional group, and we're going to start numbering from the right. Okay, so if you had, let's just say like when might you use the numbering of the alkene? It might be like a tiebreaker if you had 2 alcohols in the molecule or something like that. But largely, if there's 1 alkene and 1 alcohol and even 1 alkyne, you're going to try to give the OH carbon the lowest number. Okay, so the front end of this name looks the same. And again, carbon 4 is a chiral center, but we don't see the wedge dash, so we can't assign the stereochemistry. The alkene between 5 and 6 does not have easy geometry because carbon 6 has 2 methyls, so there's no stereochem to include here. So the front end is still 4,6-dimethyl. Okay, and then we have our root name, which is hept, indicate the position of the double bond, which is carbon 5. Okay, so hept-5-ene would be our parent chain. We're going to remove the E ending and then put in our 3-OL. Okay, so 4,6-dimethyl hept-5-ene 3-ol. Okay, our next example is going to show us how to name a diol. Okay, so remember that when we name dienes and diines, same rules apply for diols. We're going to keep the E ending of the parent alkane, and we're going to try to give the lowest set of numbers to the diols overall. Okay, so for that reason, we are going to number from the right-hand side. Okay, so the numbers assigned to the OHs are more important than the collective set of numbers overall, right? So in other words, the number at the ethyl group, the ethyl substituent, is irrelevant. I'm going to get a lower set of numbers to the alcohols if I number from the right, so that's 2 and 6. It would have been 3 and 7 had I numbered from the left-hand side, which is a higher set of numbers for the OHs. Okay, so then in the written name, we have our ethyl group at position 5. Oops. Okay, so 5-ethyl. Parent name is octane. Keep the E ending. We have the alcohols at 2 and 6 to 2,6-diol. So just a note that you keep the E of the parent alkane or alkyne, just like you would have when we talked about naming dienes or dienes, etc. Okay, and then our last example is what do you do if it's a ring? So if you have an alcohol in the ring, that carbon that bears the OH is going to have to be the lowest number, and then you're going to count towards the substituents to give the lowest set of numbers to the substituents. Okay, and so here we have a cycloheptane ring, so it'll be a cycloheptanol ring. In this case, we don't need to include the number 1 when there's only 1 alcohol in the ring, just like if there was 1 alkene within the ring. And so in this molecule, it'd be 3,3-dimethyl, and then our parent name is cycloheptane. And in this case, we don't need to include the number because it's assumed to be at position 1 as it's the highest priority functional group. So 3,3-dimethyl cycloheptanol is the name there. Okay, so that's all the naming. You can look into the workbook or the textbook to see other naming examples, where we've mixed alkenes, alkynes, and alcohols all kind of together in different iterations. So you want to take a look at that just to make sure you can combine all the rules we've now learned so far. And I think this is the end of our nomenclature packet for the semester, so we won't have any more formal naming However, there is a section of naming in chapter 11, which was for ethers. We just won't cover that in our class. You could look at that on your own if you wanted. Okay, so let's go back to our notes and learn more about alcohols. Okay, so we talked about how alcohols are a hydroxyl group attached to an sp3 hybridized carbon. Okay, so a few of the things that I want to recall. So one is the classifications. I'll just remind you again that you should revisit primary, secondary, and tertiary alcohols if you don't remember, although hopefully you can remember because they were the same classifications for alkyl halides that we used all last chapter when we were looking at the substitution and elimination reactions. Okay, so let's go ahead and think about some other properties of alcohols that might be useful to know as we move forward in this chapter. Okay, so the first is the acid-base properties. Okay, so acid-base properties of alcohols. Okay, so the first question I'm going to ask is, well, what do you think about an alcohol? Is it an acid or is it a base? Well, it could be either, right? It's very much dependent on what you're mixing it with. So alcohols can act as either acids or bases. Okay, so can participate as either an acid or a base. So it will depend on what else is present in our reaction. Okay, so here's an example. Let's take, some alcohol and let's react it with HCl. Okay, so if we reacted an alcohol with HCl, would the alcohol be the acid or the base? It would be the base, right? Because it's less acidic than our HCl, which is a strong acid. Okay, so we can revisit our acid-base properties or acid-base mechanisms. Okay, so we're going to generate the conjugate base or the conjugate acid of our alcohol, which is this, and then the conjugate base, which would be our chloride anion. Okay, so here we have conjugate acid, conjugate base. Okay, so here we can see that the alcohol could act as a base. Let's see an example where the alcohol acts as an acid. Okay, so let's choose a different alcohol here. Let's look at propanol. I'll go ahead and draw that bond in so we can write the mechanism. And let's react it with NaNH2. I guess I'm going to make that equilibrium. Okay, so now our alcohol is going to act as the acid, and our sodium amide will act as our base. Okay, so in this case, we flip-flop the roles as compared to the previous example. Okay, so let's generate the conjugate base of our alcohol. So these were what we called alkoxide anions. And then we also generated ammonia. So let's put our counter ion sodium there. And then we also generated our conjugate acid, which is ammonia. Okay, so we have our conjugate base and our conjugate acid. And I'll remind you that these we call alkoxides. And you could be more specific about the type of alkoxide by naming the parent alcohol and changing the all ending to alkoxide. For example, the alcohol we were looking up here was propanol, and so this would be propoxide, right? Okay, and we saw examples like T-butanol and T-butoxide, ethanol and ethoxide. So that's how we can name those conjugate base of alcohols. They're alkoxides. Okay, so specifically I want to take a few minutes to talk about the acidity trends of alcohols. Okay, so let's go ahead and do that. So the general pKa of alcohols is in the 15 to 18 range. But what is governing that difference between 15 and 18? 3 orders of magnitude is a pretty significant difference in terms of pKa or in terms of acidity. So let's go ahead and look at a series of alcohol and related species to think about the pKa's. Okay, so we have H2O, we have ethanol, we have 2-propanol, and we have T-butanol. So if I were to give you the pKa's of each of these, go and look them up, we would get 15.7 for our alcohol, we'd get 15.9 for ethanol, we'd get 17 for propanol, and we'd get 18 for T-butanol. Okay, so let's think about what might be governing the acidity of these various hydroxyl groups. Okay, so the ethanol from this molecule over, we're talking about alcohols and we're using water kind of as a reference. Okay, so basically if we look at the steric environment of the OH, that seems like it might be a clue as to, what's governing the pKa trends, because as I go from, the least hindered to the most hindered alcohol, I increase the pKa. Okay, so the trend is this way. If we just follow the pKa's, we have increasing acidity. Oops. Hey, that was the first time I did that today, so I think that's pretty good. Okay, so increasing acidity as we go from right to left. Okay, so remember that usually acidity trends can be accounted for by the stability of the charged species, whether that's the conjugate acid or the conjugate base. So let's go ahead and think about the conjugate base of these structures. So I want to look at T-butanol specifically because that's the one that we'll use to explain. Okay, so we're thinking about the stability of that anion, okay, that oxygen anion. Well, what is the deal with these alkyl groups? Okay, because this is likely an inductive effect, right? Because there's no resonance, that for any of these alcohols that we're looking at in the conjugate bases. So what is the role of those extra methyl groups in T-butanol and then that conjugate base that we have drawn? Okay, well, it turns out that alkyl groups are donating. Okay, so alkyl groups are donating through induction. So alkyl groups are electron donating through induction. Okay, so if they are electron donating, what are they doing to the stability of that anion? So they would destabilize the anion. So they destabilize the anion of conjugate base. Okay, and that would account for the trend that we see in the acidity. So, T-butanol over here has more alkyl groups that would destabilize our conjugate base as compared to 2-propanol, which only has 2 methyl groups that can donate electrons, compared to ethanol that only has 1 alkyl group, compared to water that has none. Okay, and so that destabilization through induction can account for the differences in pKa that we see across a series of alcohols. Okay, so now that we're on, the subject of, acidity, generating the conjugate bases of alcohols, like we did up in this example when we generated propoxide. So generating the conjugate bases of alcohols, in other words, preparing the alkoxides, is an important synthetic reaction because we could use alkoxides as a nucleophile in SN2, like in Williamson ether synthesis, for example. We could also use these alkoxides as bases, in other contexts, whether it's E2 or some other reaction that requires an alkoxide base. And so the first reaction we're going to learn of alcohols is actually somewhat of an acid-base reaction. And so we're going to think about different ways that we could prepare synthetically the alkoxides. Okay, and then from there, we're going to talk about then, the more fundamental reactions of alcohols being the functional group transformations, like what can I turn an alcohol into? And then what we'll see in that section of the reactions of alcohols is that we have a lot of similar mechanisms as we saw in last chapter. So a lot of the reactions of alcohols can follow these substitution and elimination reactions. And so we'll talk about how we can, think about OH as a leaving group, or how we could modify it to make it a leaving group to allow those substitution and elimination reactions to proceed. Okay, so the first one that I was mentioning is, let's talk about the preparation or the synthesis of alkoxides. Okay, so synthesis of alkoxides. All right, so remember that in alkoxides, so I'll abbreviate that or give that a structure. So alkoxides are the conjugate bases of alcohols, so conjugate bases of ROH. Okay, so how would we prepare those? So we basically are going to have 2 general ways. One is that we're going to mix our alcohols with sodium. Okay, so Na0, sodium metal. Okay, and the product of this reaction would be our alkoxide anion, and then our alkoxide anion, sodium cation. Okay, and then we liberate H2 gas. So you might be thinking, well, if I just want to make an alkoxide, why don't I just simply do an acid-base reaction? Well, as we looked up above, those acid-base reactions are at equilibrium, right? Well, look at this reaction. So we liberate H2 gas as a part of this reaction. Okay, and so when we do that, it's an irreversible, essentially an irreversible reaction. I can't shove H2 gas back into the reaction to do the back reaction. Okay, so this is an irreversible reaction to generate the alkoxide anion. Okay, and so that's why it's synthetically useful, because it's irreversible. We'll get basically 100% conversion to our, product alkoxide. Okay, so in addition to sodium, you could also use, sodium, lithium, or potassium would work here. So I'm going to write that all again. Okay, so sodium, lithium, or potassium could be used here. All right, and so we're not going to look at the mechanism of this. I think it's in our textbook, but it's a free radical reaction where our sodium is giving up electrons, a single electron transfer to our oxygen to generate the oxygen anion. So you could go ahead and look at that if you were interested, but we're not going to look at that mechanism in our class. Okay, so let me give you the second way to make alkoxides, and then we will look at them in context in terms of, a reaction or a synthesis. Okay, so the second way is we're going to take our alcohol and we're going to react it with sodium hydride. Okay, so NaH is sodium hydride. Okay, and this is actually an acid-base reaction. Hydride, H- is a base. Okay, but let's think about if we used hydride as a base. I'm just going to go ahead and put the mechanism right on here. Notice how we would generate our alkoxide anion. Okay, but then what is the conjugate acid of hydride? Well, it's H2 again, right? So here's another example of an irreversible acid-base reaction. So again, once I have generated H2, it is a gas and it bubbles away. It's out of solution, and I'm not shoving that H2 back into solution, and so this is an irreversible acid-base reaction. So both sodium and sodium hydride basically do the same thing in making those alkoxide anions. And the choice of which one you use doesn't really matter. Okay, so let's think about how we might use this type of reaction in context. Okay, so let's imagine we wanted to prepare an ether. Okay, and our starting material, so let's just say we started with this alcohol, and through synthesis, we wanted to make this ether. Okay, well, we really have two options, right? So if we assume this happens through Williamson ether synthesis, we could generate this oxygen-carbon bond or this oxygen-carbon bond through an SN2 reaction. Okay, well, we already have the oxygen, that's attached to this carbon over here. So in my mind, it would make sense to make this oxygen-carbon bond through the SN2. So what would be required is that I generate the alkoxide of the starting material that I was given, and then we can perform the SN2 reaction by coming up with the appropriate alkyl halide. Okay, so I'm going to go ahead and just number my carbon and oxygen atoms. So I'm not numbering this for naming, but more so to keep track of the atoms in our product. Okay, so let's just make this then 6 and 7. So essentially I want to make the bond between oxygen 1 and carbon 6. So I'm going to generate the alkoxide at 1, and then I'm going to basically add in the appropriate ethyl electrophile. So we could use something like ethyl bromide. Okay, so I'm going to show this in 2 steps, but you could really do this in a single step when you're considering synthesis, when you're practicing doing that. Okay, so at this point you could use sodium hydride or sodium, lithium, or potassium. Those are, equivalent here. Okay, so we've generated our alkoxide anion, and now we're going to react with ethyl bromide to do our SN2. So you can throw in your favorite polar aprotic solvent, and we'll do the SN2 reaction. Okay, so just to write the mechanism down below in case you were, not really seeing where this was coming from. Okay, so we've basically added those 2 carbons. And so if I keep my, atom labels on there, those would be carbon 6 and 7. So I just made that bond between oxygen 1 and carbon 6 from ethyl bromide. Okay, so that's when you might want to use this type of reaction or preparation of alkoxides, is when you wanted to then use that alkoxide in, say, an SN2 reaction, or, if you needed to generate the base for an elimination reaction or something. Okay, so the next series of reactions we're going to learn in this chapter are going to focus on the substitution and elimination reactions of alcohols. All right, so let's just get a new page here. So we're going to think about really the functional group transformations of alcohols. So if I just asked you, as an example, would this reaction be possible? So could I do this reaction? So let's say I wanted to do an SN2 reaction with DMSO. Would that be possible? Why or why not? So it would not be possible, right? There's no reaction there. So what is the problem with alcohols in these reactions? Okay, well, it would not occur because of the leaving group, right? Hydroxide is a bad leaving group. Okay, and so we can't do the substitution and elimination reactions directly on alcohols. Okay, but there are a few things that we can do to the hydroxyl group to make it a better leaving group. Okay, and we're going to see that really in the next couple of reactions that we learn. All right, so let's go ahead and introduce our first reaction. So our first reaction is going to be the reaction of alcohols with HX. With HX, where X is going to be chlorine, bromine, or iodine. Okay, so what is the first thing you think about when you see, say, HCl? Hopefully it's like, oh, it's a strong acid. Okay, well, earlier today, we looked at the reaction between an alcohol and HCl, right, as an acid-base reaction. So that ends up being relevant when we think about the mechanism, right? So let's go ahead and draw out the schematic of this reaction, and we'll talk about, some of the properties of the reaction overall, and then we'll look at the mechanisms. Okay, so here is our example. Okay, sorry about that. I had a sneeze attack. So anyway, let's look at the overview of this reaction. Okay, so we're going to take our alcohol and we're going to react it with HX. And HX is going to be both the reagent and the solvent here. And what we're going to see is essentially a substitution reaction where we have substituted our X group for our alcohol. Okay, so we basically have replaced the OH, the hydroxyl group, with whatever our halide is. So this looks like an SN2 reaction, right? Or an SN1 reaction, some sort of substitution. Okay, so we're going to take an alcohol and we're converting that to an alkyl halide. All right, so let me tell you a little bit about this reaction. So not all alcohols are equivalent in this reaction. Okay, so it turns out that primary alcohols are moderately useful. Moderately. Sometimes you write a word and it looks like it's spelled incorrectly, but I'm pretty sure that's right. Okay, secondary alcohols are not very useful, so we'll say less useful. And tertiary alcohols are also useful. So we'll say these are the most useful. Okay, so what does that mean, useful? Okay, so useful basically means in the terms of, organic reactions that I can perform that reaction and I can get a high yield of the product that I want. So in this case, it's the substitution reaction where I've converted the alcohol to the desired alkyl halide. Okay, so it's weird though, right? That the trend is primary is good, secondary is bad, tertiary is good, right? Because all the other reactions that we've seen, so let's assume it goes by an SN1 mechanism. Well, in an SN1 mechanism or reaction, primary is bad, secondary is okay, tertiary is good. Or for secondary, or for SN2, it would be the opposite, where tertiary is bad, secondary is okay, and primary is good. Okay, so what is this trend where it's good, bad, good in terms of the substitution? So what that indicates to us is that there isn't actually a change in mechanism as we go from primary to secondary to tertiary. Okay, and so we're actually going to see that this reaction with HX follows either an SN1 or an SN2 mechanism, and depending on whether it's primary or tertiary will determine whether it's SN1 or SN2. The problem with secondary is that it's confused, just like it was back in chapter 9. Secondaries can undergo both SN1 and SN2, and so we would get a mixture of both of those reactions, and if it goes by SN1, we could get these carbocation rearrangements. So the secondary alcohols just end up being less useful for that reason. Okay, so I want to go ahead and look at the mechanism for primary alcohols. Okay, so primary alcohols with HX. So let's look at this as an example. So we'll take ethanol and we want to convert it to ethyl bromide. So I basically am doing the the backwards reaction of SN2 that I learned from the bromide or from the alkyl halide to the alcohol back in chapter 9. Okay, so a primary alcohol. We know that primary electrophiles prefer to undergo SN2 reactions. So, we still have this problem that our alcohol or hydroxide is a bad leaving group. Okay, so let's think about what the first thing that might occur with our alcohol in the presence of HX. Okay, so when our alcohol is in the presence of HBr, we would first do the acid-base reaction. Okay, so whereas hydroxide was a bad leaving group, what would be the leaving group for the following molecule? Okay, so let's just imagine then, if our nucleophile were to attack this carbon, OH would be the leaving group. If the nucleophile were to attack this carbon, the leaving group would be what? Well, it'd be water, right? Water seems like a pretty reasonable leaving group. It's a neutral, stable molecule. Okay, so that's exactly what happens. When we protonate the OH, we turn the OH into OH2+, and that makes water the leaving group. So we've now just converted to a good leaving group. And now we can proceed with our substitution or elimination reactions. Okay, so water is going to be our leaving group. So let's take our nucleophile bromide that we just generated and attack the carbon and have the leaving group leave. Okay, so what type of mechanism did I just draw? Well, it was a concerted mechanism of bond making and breaking. So this is an SN2 step. So we have an SN2 step within our mechanism, right? And that directly is going to give us our product. And then we'll generate water as our byproduct leaving group. Okay, so again, this is SN2 because our leaving group is attached to a primary carbon, okay? And so we do that SN2 mechanism. Okay, so we're gonna skip over secondary for now, and let's look at the mechanism for tertiary alcohols. And this is after we look at this mechanism, we'll go ahead and be done today. All right, so let's just take a easy to draw tert-butanol and let's react this with HBr. Okay, so our product would be this tertiary bromide. Okay, so again, we can't directly do an SN1 reaction on our alcohol. So the first thing we're gonna do is protonate our OH to turn it into a good leaving group. Okay, so once we've protonated, we will have a good leaving group. Hold on just a second. Okay, I'm back for a third and final time. That interruption was because of a 3-year-old and a 5-year-old who will remain nameless at this point. So anyway, where we're at in the mechanism is we were looking at this tertiary alcohol and its reaction. So again, the first thing we're gonna do is protonate to turn that OH into a good leaving group. Once we're at this point, now we have basically this tertiary carbon attached to a good leaving group in that H2O, that water molecule. Okay, and so we know that these tertiary electrophiles will not undergo SN2 reactions, and so from here we're going to follow our SN1 mechanism. Okay, so what would be the next step if this is following an SN1 reaction? Well, we would have our leaving group depart. So we can show our carbocation, and so here you will check for rearrangements, right, and make sure that you nothing funky is going on there. And then from there, we'll have our nucleophile attack. Okay, so our nucleophile will be our bromide, and that can attack and generate racemic mixtures. Okay, so for this part of the mechanism was SN1 with the leaving group leaving and then the nucleophile attacking. Okay, so there's the mechanism for primary and tertiary. Again, secondary alcohols are not particularly useful because they give rearrangements and they undergo a variety of different mechanisms, including SN1 and SN2. Okay, but it turns out that not all is lost because we're going to have very specific reactions that we'll learn about on Friday, which will allow us to convert secondary alcohols to the corresponding bromide and chloride using a different reagent. Okay, so that's where we'll stop class today. So in class on Friday, we'll look at other ways to convert alcohols to alkyl halides, and then we'll also probably look at the elimination reaction, which is called dehydration. We'll look at dehydration reactions of alcohols. All right, so I'll see you guys all on Friday. Hope you guys have a good couple of days.